So thanks for your introduction. So I'm Pierre Rouanet. As you just mentioned, I'm one of the co-founders of Pollen Robotics, and we have been recently acquired by Infex, and I was thinking this is quite interesting to mention because I think it's quite related to what I want to talk about today, which is really what's happening at the intersection between those two worlds, which are robotics and AI. And so my background is really on the robotics side, so I will give mostly the robotics point of view, but I think this is interesting because I'm guessing in the room there is much more of the AI side. And so I spent the last 10 years or so building this kind of robots, so humanoid robots, many different kind of robots, working on the effectors, on actuators, etc. And I've, as many of my colleagues in robotics, we've really seen how much AI made a huge impact on what we can do with robotics, what they can perform, where they can go, etc. But also, I want to mention also kind of the other way around, which is we've seen more and more people from the AI community using robotics to try to test and evaluate their system into the real world. And so if I'm zooming back a bit on the history of robotics, you can see that in the last 10 years or so, we've really seen like this big trend of robotics coming from the factories, where there is like really everything is really constrained, everything is really set up. You know exactly where everything is located. You know perfectly the position of your robot. You know what's going to be around. You know the task. You know pretty much everything, right? And as basically the only kind of interaction that you can have is if something goes out of the plan, you just freeze and stop and basically call an engineer so he can fix the problem and you can go back to your routine. So it's much more about automation. But more recently, we've seen like this changes, especially I can mention like this kind of action robots, autonomous vehicles, where we kind of shift forwards to more like more uncontrolled environments. But I mean, the road is still our way to make those environments much more predictable. So this is kind of a trend, and nowadays we see like many of the big players, big research labs, big companies really wanted to move towards like having more robots closer to our home, closer to ourselves, and much more reactive and interaction things going on. And I think most of these paths that we made and most of the progress that we made on those robotic side, there is some huge progress that were made thanks to LLMs and VLMs. And especially, I mentioned here like two big domains, like the first one being like the visual perception, which is obviously something extremely important when you're talking about robotics and when you're talking about adapting to the environment. You need to be able to detect what's around you. You need to have context, to understand it, so you can analyze the situation, act, and react to it. And once again, like this kind of VLMs, they're really shining because, for instance, if you just want to, let's say, grasp a glass of water, well, there is not a very specific shape for glass. You have many different shapes, you have many different textures. It can be located at very different locations. So you need this kind of really zero-shot approach where you can really adapt and adapt to what's in front of you. And the other obvious big improvement that we've seen is through the interaction. I mean, nowadays we can have like LLM directly plugged to the robot, and you can use some very natural prompts. For instance, in this case, I think the prompt is something like grab me the orange and put it into the brown bag. And you can have like the LLM like figure out all the context detail that you need, all the basic subtasks that's needed to really perform this like underlying tasks. And another big domain that I want to mention where we've seen tremendous progress on the robotics thanks to AI is really like the locomotion. I mean, back when I was still a PhD, like about 10 years ago, locomotion was still considered as an extremely complex task. I mean, it really is complex. But we've seen some huge progress where nowadays you have like many different companies, many different research labs that manage to have like humanoid robots doing those crazy, not only walking, but running, jumping, doing kung fu. For quadrupeds, it's even more crazy what they can do. And most of the progress, in my opinion, that was made on those fields is really thanks to the use of pretty standard, actually, deep reinforcement learning algorithm. but with really powerful simulation tool that can really closely mimic what's going on inside the robot, what's the physics of the motor, how they're actually behaving, etc. So we're really closing the sim-to-real gap in this field. And also something that I want to mention, because it will be important for the rest of our presentation, is even if this seems like completely crazy and extremely hard to do, this is also a problem where you can have like a really well-defined and really well-understood reward function for your robot. If I'm being a bit too simplistic, but for the sake of understanding, you can imagine that basically your reward function is something like I want the robot to follow this specific trajectory and add some kind of constraint, like I want to get my to keep my head straight, so not to fall or to keep my balance or this kind of things. And actually, where we're still really struggling, and this seems like a bit disorienting, because I mean, most of you can clean your kitchen, and I'm not sure that all of you can do kung fu. But for robotics, it's really the opposite. Cleaning a kitchen is actually a way harder task in a sense. And once again, what I'm trying to tell you here is that this kind of task is much more in control, much more generalized in a sense. First, you have to deal with like low-level generalization. Once again, you have many different plates. They can have different shape, different texture, different weight, different physical interaction. Same for all the objects you will have around. All kitchens are configured a bit differently. And actually, what you've seen in this video is like really state-of-the-art made by the Physical Intelligence company, which is like one of the big names in the manipulation in robotics. And what they've done is like they use their robots and put it in many different apartments in San Francisco to train it on different configuration. But still, you see that like this is like a really clean kitchen, really kind of formatted already. But still, this is where we're trying to go and where we're still struggling. Another important thing that's trying to explain why this is more difficult is that this cleaning task is not so well defined. If I'm asking, I don't know, 5 persons in the room to clean that kitchen, they will probably come to slightly different solutions, slightly different results, and the path along the way will be slightly different. And probably also an explanation for that is that you need like longer planning. For the locomotion, basically what you need is like to plan basically in the next step or so. So plan like a few seconds in front of you, but that's it. For this kind of task, you need to plan like 30 seconds, 1 minute ahead, and that's where we're still really struggling with the existing model. And probably one of the big reasons, I mean, that's how it has been in AI for many of the big problems that we have, is that we lack data. So I'm not saying this is the only issue we have, maybe there are some other issues, but at least we are certain that we need more of this kind of data. And actually, I think this is kind of different data than what we have at the moment, and it's not as easy as just scraping the whole internet and getting a lot of videos, because what we probably need is more like some kind of embedded first-person egocentric point of view, where you really the subject of the task you're trying to solve. Those kind of videos should be way more interactive, way more reactive to what more the static kind of data set that we're using at the moment. So really to encapsulate this kind of physicality, this kind of reactivity of the world that we want to try to understand better and to use. So what you can see on the top of my slide is like examples of people trying to use robot and teleoperation in particular to collect data directly on the field. So once again, you can imagine that most of the big names in research or even companies at the moment are buying their own fleet or building their own fleet of robots and having the operator running on the cloud just performing this kind of task and recording a lot of data. But obviously this doesn't scale that well, especially if we don't really know how much of this kind of video we need, but probably in terms of millions or so. So it will probably take time and it will be hard to do. So there is also a lot of work on simulation, also on directly working with like more human performing task videos. But then again, you have like this kind of simulation or simulation to the real world or the human to the robot gap, which is not that easy to cross. and it's not that certain that we can go that way. And actually, there is a lot of discussion at the moment in this field. I mean, this is also a discussion that's happening in many other AI fields as well, but about the data recipe. Basically, you have like research paper just telling, okay, I'm using 10% of on my whole database, I'm using 10% of real-world data from robots. Is that enough? Should I use 20 or should I use more of that, etc., etc. And I think on the other way around, and that's actually a quote I put from Sergey Levin, which is one of the big research names in manipulation, in robotics. And the idea is that if we manage to have like this kind of useful robots in a real world doing some useful tasks, well, obviously that's good because they can perform the task, but it will probably also become the kind of the primary way that we acquire new kind of data, this kind of really interactive kind of data that kind of encapsulates the physicality and the way that we deal with the world. And so I think this is really interesting, and I wanted to put it there because I think this is also probably where the AI and robotics field will cross more in the future. And actually, well, I mean, I'm not going to explain a lot more why we need open solution. I mean, Matthew did like a keynote on this topic just before. But I think this is particularly important that we still mention it, especially when we're talking about robotics, because there is still this hardware that we need to get in order to get started, and it could be costly, it could be hard to build, hard to maintain, it could even be threatening. So there is really a lot of effort that we need to make in this direction in order to have like a really many different communities, many different people from different fields working on those topics, and not just only big robotics labs or companies. And so actually that's how I want to kind of conclude my talk, is by presenting you like three main projects that, in my opinion, are kind of a good way of starting this kind of process and going into that direction. So the first one is a really low-cost manipulator arm made by mainly by the Robot team. So maybe you've seen they're just building a hackathon just in a hallway, and so you have like I don't know 20 or so people like building the robots for the last couple of days. And the idea is really that anyone can buy or build itself this kind of robot. So you have like the 3D plans, you can 3D print it yourself if you have access to a 3D printer, or you can order the pieces online. You have the bill of materials with all the motors and electronics that you need. And it's directly compatible with their library, so you directly have access to like the really state-of-the-art end-to-end learning algorithms. So for instance, they have a full tutorial where they show you how you can train your own robots to fold your t-shirt, for instance. And they already have like thousands, I've put 100, but I should update my slide, it's probably around 1,000 now, of people around the world, like they build their own robots and collecting their data set, etc. Another kind of project in the same kind of parallel way, but this one is much more about locomotion, and it's actually a project led by Antoine, which is in the room. And the idea was really, I mentioned before like locomotion, but you can imagine that the big humanoids or the big quadrupeds are still quite expensive. They are quite complex, they can break, they're even dangerous, they are really powerful. So the idea was really to build something like really low cost that anyone can access, can build. And so he came up with this robot, which is really inspired by the Disney one, if some of you may have seen it. Once again, the idea was really to let anyone start training its own robot and start replicating this kind of result to better understand how we can train robots for locomotion. And they also spent quite a lot of time working on this kind of sim-through-wheel problem, which is especially critical when you're talking about like really low-cost robots which have motors that can behave quite randomly, let's say it that way, or at least it's harder to predict how they're going to behave. It's evolving over the time, etc. So they spend a lot of time better understanding this and having like a simulation that's close to the real one. And actually, what you see on the left of the slide is like the same learn policy in simulation running directly on the real robot. And actually, they wanted to go even further than that. And the idea was really, okay, so we have this robot and we can train it how to work. But what about if you want to build your own robot or your own design, and how we can make this pipeline so to go from your very basic idea to the CAD design, then to the simulator, and then to the real robot. And how can we make this process as simple as possible and as quick as possible, so you can really iterate and try new things and yeah, have a lot of variety of robots trying to learn this stuff. So thanks a lot for your attention. So I really wanted to give you like an overview of what's happening between those two fields. And if you're interested in those projects, actually the robot from Antoine can be seen across the hall. And Charlotte is also going to make a talk this afternoon about this robot and how we can use LLM to make it more expressive through emotions. And you can find all those projects on the Discord, GitHub, etc. And yeah, and if you have any questions.